of carbon-carbon pi bond. And we know it is excellent source of electrons. It is a nucleophile. So we are looking at reactions that as a class, we are calling them electrophilic addition. Basically, by electrophilic addition, we mean we are going to get rid of the pi bond. We go from sp2 hybridized to sp3 hybridized carbon. Now, when it comes to these reactions, they are regioselective. The fact that you hear Markovnikov or anti-Markovnikov, it means that electrophile will choose one of the carbons of carbon-carbon double bond. And the nucleophile chooses the other. So this time they have a choice, and they are very, very choosy, guys. Remember. Now, if you just remember my principle, the electrophile always goes to which vinyl carbon, guys? Less substituted. If you remember this, you don't have to be worried about Markovnikov or anti-Markovnikov. Now, to get started, let's start with something like this. And add HBr. In this case, is there such a thing as Markovnikov or anti-Markovnikov gas? Absolutely not. You have two identical carbons. So because you have two identical, everything is going, and I'm going to tell you right now, this is a lousy experiment. Okay? I'm going to tell you right now. Why it is a lousy experiment? Because there is no difference between these two carbons. So, what will happen? You can get Br, and you also can get, assuming that your Br goes to that carbon. If Br goes to that carbon, assuming that Br goes to that carbon, what else would you expect to get from the same position? Diastereomer. Remember, this time you don't get an enantiomer. Why you do not get an enantiomer? Yes. Why you don't get an enantiomer? You had a pre-existing stereocenter. Did anything happen to those stereocenters? No. Okay. So because your pre-existing stereocenters still do exist, these two, you call them what, guys? Diastereocenters. And this is the only reason that I am using this molecule in particular. From the very beginning, I gave you a hint. It is a lousy experiment, and I will show you why I am saying it's a lousy experiment. Because at the same time, your VR could go which also would get another, which it is diastereomer. And you and I commonly do expect a side product, but we hope that side product be major. So we have one to be major, the side product be minor, and we have a major. But here, can I say any of these is better than the other one? No. So I may get 4 products, 25% each. Worthless, literally, worthless reaction. This is one. The second one, anytime you have cation, what would you expect? Yes, if you have cation, what do you expect first? The arrangement. If there is cation, you can have carbocation rearrangement. So what it means that I'm just looking at the mechanism for one. Obviously, I am not going to show all of the mechanisms. So obviously, next step, boromide is going to be added. You will get those two. Or you have carbocation. What would you expect? Rearrangement. Going from secondary And again, I don't have to tell you that when hydrogen moves there, it could be R or S. In this case, no, it won't be. Well, it won't be. And because both are hydrogen, so I don't have to be worried. Two identical groups. But now what happens when boromide goes there, guys? A mixture of R and S for your cation. So basically boromide can attack, I call this A, or it could attack on the other side. So, these are the possibilities. Keep in mind, if you have carbocation, you are generating a stereocenter. That stereocenter could be or this. Now, one thing that students always ask, when should I be worried about carbocation rearrangement? And when I should not? It depends on the nucleophile. For excellent nucleophiles, such as bromide, iodide, cyanide, the nucleophile that we know them as good or excellent major organic product will be the product without rearrangement. So this nucleophile, you will get major product without rearrangement.
Question, Professor?
Yes.
It's because they're good or strong nucleophiles that there's no time for rearrangement to occur, is that it?
They move faster, absolutely. Because these are all, you know, such a thing as a rate of reaction. So they trap the cation before it undergoes a rearrangement. On the other hand, for nucleophile or fair nucleophile, fair or poor nucleophile. If you have fair or poor nucleophile, major organic product is going to be the product of the arrangement. Now you can guess what is a fair nucleophile, guys. That is poor. A fair nucleophile. Poor nucleophile, as you said, water, alcohols, carboxylic acid. So that being said, I'm going to ask you, like major organic product, like major organic product of this reaction. And I'm hoping that you have. I'm going to label carbons. That obviously, if you were going to number your carbons, that would be the order that you would be numbering, wouldn't it? 1, 2, 3. Question. Am I assuming if you were going to number, that's how you would number? Lowest possible number. Your functional group are carbon-carbon double bond. Carbon-carbon double bond wouldn't make any difference. Either way, your number is going to be 1 and 2. But if you go from B to A, then your substituent will be carbon number 6. Whereas if you go this way, your substituent will be number 3. So keep in mind, always the lowest possible number. That keep in mind, functional group comes first, everything else comes second. Now, in this case, the covalent will be bonded to which carbon gas for major organic product? Carbon number 3 acid. because you are going to have carbon rearrangement, it doesn't matter. It doesn't matter whether you add H to B or A. One way or the other, you is going to rearrange to get to the more stable cation, which it is. I'm not writing the mechanism. I am assuming you guys know it. The only thing I will remind you that every step reversible. And if you are not sure, please come and see us during the office hours. So these are the principle of addition of HX. Now, of these HXs, one of them, are you noticing I really wrote it big? Okay. One of these can do both ways. What am I talking about? What would you expect to be measured organic product here, guys? Would you expect bromine to be bonded to internal vinyl carbon or terminal vinyl carbon? Internal. So this is what we would expect as measured. Now, a scientist did this reaction and got exactly the opposite. And obviously, when you get something that has never ever before have been reported, the first question you are asking yourself, what am I doing wrong? I'm serious. If everybody else has done something and has constantly reported something exactly opposite of what you get, the very first question, I don't know about you. At least I can speak for myself. The first thing I ask, what am I doing wrong? And unfortunately, these days I am used to it, and I'm going to tell you why I'm used to it. I was not born with a cell phone in my mouth. I was born with my toy in my mouth. That new generation, I don't have to tell you. So, anytime I'm using those kind of electronic devices, they all are against me. Regardless of the brand, regardless of how much I pay. And the first thing I do, I call the technical support, and I'm saying, I don't know what am I doing wrong. And they are so used to, now they are trying to build up confidence in me. And they say, oh no, and other people have reported the same problem. That I say, okay, the other people are 6 years, 7 years old. They have a lot more confidence in themselves. They know they are doing everything right. It's you. In my case, I think I'm doing everything wrong. So it's me. Truly. So I can really, so I'm very good in accepting all responsibility, and constantly is my fault. Now, when that scientist found that using this got exactly opposite, then the question was, what am I doing wrong? So you go and check your notes, and you say, hey, you did the same thing, you followed the recipe, you took butane, and then you would think, okay, let's look at the way they did it. So they did go back and read Markovnikov's note. Markovnikov had said, before doing the experiment, he distilled the alkene to make sure it is fresh and pure. I go and read the label. I thought it was 99.9% pure. And all of a sudden, I see it is expired. It was 3 years ago. So that alkene was sitting on the shelf. Now let me tell you what will happen. When alkene stays on the shelf for several years, they are being oxidized. And they are forming something that we call them peroxides. So basically, this alkene over time, as time has gone by, it has been oxidized. And because it has been oxidized, it has produced something that we call it peroxide. And right now, I am going to tell you guys, peroxides are extremely weak bonds. Peroxides are extremely weak bonds. So because they are weak bonds, they easily break up. So what in reality has happened, I'm not going to show you the mechanism for formation of peroxide. Of course, there are more details because you and I know carbon mass have how many covalent bonds, guys? 4 covalent bonds. So you are going to get peroxide, and your carbons are going to be 4 bonds. But that's another story beyond our conversation. The only thing that it is important for us to remember, only HBr, not HCl, not HI, they do not undergo entire Markov-Nikolai. Only HBr undergoes. So you know, M stands for Markov-Nikolai gas, is that right? So when we are using HBr, in presence of peroxide, I don't have to tell you guys, we are always exposed to UV light. This is nature. Okay, guys? There is always UV light available. What will happen? We'll do exactly opposite. Remember, H was supposed to go to terminal carbon. That was Markov-Nikolai. That I asked you, just don't say H, say what, guys? Electroviolet. Because if you understand the principle of electrophilic addition, you don't have to be worried. So how does the reaction work? Well, you just heard me. I said peroxides are very weak bond. You are going to break your peroxide bond into what species, guys? What do you call this? Free radicals. Species that they are not charged, they have unpaired electrons, extremely reactive. Once you have radical, then due to the fact that radicals are extremely reactive. This is something that in CHE118A we were calling it propagation state. It provides the next reactive particle. So this is not your electrophile. Wouldn't you call electrophile any species that it is electron deficient? Don't forget, elements want to have full valence shell. It doesn't matter whether it is very radical group of atoms with not full electron, or atoms. Either case, they are electron deficient. So the second propagation step happens. Don't forget, again, I repeat. We know that a pi bond is source of electron. So your pi electron is going to react. Please keep in mind about arrows. We are talking about single electron. And I'm going to tell you, when it comes to mechanism on exams, it's either my way or no way. Okay? So with mechanism, guys, please do not come to me and say, look, I wrote part of it. If they don't make sense, it is not correct. So keep in mind the ruling. I get points for every arrow, very clear instructions to the TAs. And naturally, if you go and tell them, they will tell you, go to Nesiri. And then you come to Nesiri, I have already told you, it is either my way, you know the rest. So be careful about mechanism. I'm serious, because understanding the mechanism, it will help you not to memorize. Follow the trend of reaction. Understand the principle, electrophilic addition. Then recognize your electrophile and follow. Remember, I said electrophile always goes to the less substituted carbon. You can call it Markovnikov, you can call it anti-Markovnikov. The principle is the electrophile goes to the less substituted carbon. This time the electrophile is Br. That's why it behaves differently. You get a new free radical. What will happen when you get this new free radical? Another propagation step. It becomes a chain reaction. Free radicals always are chain reaction, and that's the main reason that we are concerned when we are exposed to free radicals. We know they cause chain reactions. That's why they are carcinogen, guys. So free radicals always are chain reaction. So another propagation step. I guess I don't have to tell you. As long as you have reactants, it's keep going and going and going. So these are as far as addition of HXs. Did you notice I didn't use HF? I said If they are good nucleophile, bromide iodide. If they are fair nucleophile, it is either water or alcohol or carboxylic acid and chloride. So this is as far as those. Next, now I'm going to talk about water. Remember, the name of these reactions is electrophilic addition. And to get started, I'm going to ask you, would you classify water as electrophile, guys? I never have heard that water be electrophile. You commonly call water as what? We just call it for nucleophile. To the best of my knowledge, you have never been told, or I hope you have never been told, that water is electrophile. So what it means? It means that first, I'm going to write the pattern. So electrophilic addition of water. We want to add water. What will happen? I am going to put a little less space, guys, so basically you'll be able to add another word. Question. What will happen if I add water to this alkene? Let them see it for centuries. Well, nothing will happen. In the first place, is even your alkene is water soluble? No. Yes. Would you expect alkene be water soluble? Mm-hmm. Don't forget, like results like, not unlike results unlike. Water very polar, perotic, alkenes non-polar. They even physically don't interact. Forget about chemical. So nothing will happen. That's why, if you want to add first, we will talk about acid catalyze. Okay? So we will do acid catalyze. Like acid catalyze, what do I mean, guys? You have to use acid. What kind of acid? Non-nucleophilic. Because you don't want to add your acid, you want to add water. Non-nucleophilic acid, phosphoric acid, sulfuric acid, hydrochloric acid. So, of course, only catalytic emulsions. And we have to use also heat. Now, when you do this reaction, obviously you will expect water. Which addition? Don't forget the reaction is regioselective. Is that right? So you would expect, now from the viewpoint of water, keep in mind, when we are talking about these reactions, obviously, when it comes to water, this is how we are looking at it. H is your electrophile, NuOH. But that being said, we know water is not electrophile, thus we are pushing it. So in this reaction, I would expect now, once I get this product, what would I expect? From this product, what do I expect? I expect mixture. Mixture of what? Enantiomer. Why I expect? So, keep in mind, in exam, I do expect that you recognize your reactant didn't have a stereo center. Your product has a stereo center. A stereo center is the result of the product. I said, if you are generating a stereo center or centers, and there was not a pre-existing center, what would you expect? So that's why either you will identify this as R and S, not R or S. Okay, that is, or you will write one with a stereo, for example, like this. And then I will put plus enantiomer. You know, it is your choice. You can put R, you can put S, guys. Keep in mind. You can write two products, one R, one. You can just write one product, stereochemistry R or S, nobody cares, as long as you write plus enantiomer. So these are your choices that you cannot ignore your stereo center. So this is that. Not that being said, do you see any problem with adding water to carbon-carbon double? Do you see any problem? Acid catalyst. Would you expect any problem? Yes. Carbocation rearrangement. So, what happens? What happens? What happens? So let me just write sulfuric acid. I don't think there's anything. What happens if I do this again?
Professor, are you saying that this one is the same as the top one? That there's three, that carbon has three methyl groups attached to it? The one above it?
I'm not saying this is the same.
Okay.
I'm doing a different reaction.
Thank you.
And I'm asking you, what happens if I do this reaction? Obviously, I am going to get multi-products. What are multi-products? Which obviously is going to be enantiomer. What else? So, if you have cation, guys, expect carbocation rearrangement, especially when you are heating. If you use heat, rearrangement happens before nucleophilic addition. When we are using HBr or HI, I told you don't be worried about the rearrangement. Why I told you don't be worried about the rearrangement? Because they are not going to be added even at room temperature. They are going to be added at 0 degrees Celsius. But once there is heat, always expect rearrangement is faster.
Isn't there supposed to be one more carbon because there's 6 carbons in the other one?
Yes, thank you.
In the other one.
The other one is going to be CH2, yes. That's the next one. Okay. It's always easy to fix if you recognize that. So now let's look at our. I'm wrong. Where did it go? I got a tertiary, it went here, so I don't get this. Okay, because I'm going to show mechanism, you will see. Anyway, so let's look at the mechanism and see what is happening. What would you expect to be the first step of the reaction, guys? Acid-base reaction. You always would expect acid-base reaction. And this, keep in mind, every step is reversible.
So the base is the pi bonds of the alkene?
Yes.
Thank you.
Let me write it like this. So you have carbocation, guys. If you have carbocation, what do you expect? Rearrangement. And I guess I don't have to tell you this rearrangement is very favorable. You are going from a secondary to a tertiary. Now that you have your rearrangement, then your nucleophile is going to be added. What do you have? Oxygen. That is positively charged. What would you expect to happen? You expect a base to come and take it away. What is a reasonable base? Obviously, another alkene is reasonable, but as time goes by, you are running out of it. Hydrogen sulfate is base. Is it really? Let's give it the benefit of the doubt. But what happens if you have sulfuric acid and water? 100% dissociation. Agree, guys? Don't forget sulfuric acid is the strongest. So the best choice will be water, because it is there from the very beginning. So last but not least, every step is reversible. Obviously, we are using hydronium ion, and we will get peroxide. So this is acid catalyte. Due to the fact that we have a problem of the arrangement, acid catalyte is not popular. The only thing that acid catalyzed will be done is when I am not going to be bothered. Carbocation. Basically, you have 98% of a cation without a rearrangement. Beyond that, guys, if there is a chance of rearrangement, acid catalyzed addition of water is forbidden. Yes.
Sorry, which reaction during the aerobics?
This is your product. Okay. Thank you for asking. Any other question? So this is acid catalyzed, which again I repeat. The only time we do acid catalyzed if there is no chance of getting a different cation, guys. A different cation. Even, don't forget, secondary and secondary are not exactly the same. What am I talking about?
Secondary and secondary, Professor?
That's what you heard me.
Okay.
Guys, are these two cations the same? Okay. If you number them, you will number them. Carbon 3, carbon. Is that right? So keep in mind, that's what I said. Even secondaries are not the same. Unless they be exactly identical. So the only time that we do acid catalyzed of addition of water is when I'm not going to be working. About carbocation rearrangement. If there is carbocation rearrangement, there is not going to be a useful reaction. So how about if I want to get the product without rearrangement? Because alcohols, it's not a secret. In organic chemistry, they are very popular compounds. They have lots of use for them. So how about if I want to do Markovnikov addition exactly the place that I want? So I'm going to use the same reactant as I used before. And I want to do Markovnikov addition. Okay. By Markovnikov addition, I don't want rearrangement. I want OH on carbon number 2. That's where I want it. Yes, I do understand I get an enantiomers. I have no control over it. That is, from the very beginning, is obvious. That I don't want structural isomers. A stereoisomer, I have no control. If I want to do the reaction this way, I have to do it in 2 steps. Step 1 is known as oxymercuration. Step 2 is known as demercuration. So, for oxymercuration, we are using commonly mercury 2 acetate. Obviously, the whole idea is to add water. So this is step 1. Keep in mind, when we are doing the reaction in several steps, we have to identify them as 1, 2, and so forth. Step 2 is demercuration. But water is there anyway. I just want to let you know. Now, here I want to remind you of your general chemistry. I don't know if you ever try to memorize a little bit about something or not. But if I teach general chemistry, I would ask students at least remember minimum about compounds that they are always water soluble. Compounds of alkali metals, acetates, nitrates are always water soluble. So this is mercury 2 acetate, that's what I called it, you heard me, which it means always is water soluble, and I'm going to give you a hint. The mechanism is slightly different from the way that the book has it. So obviously we are calling electrophilic addition. I do need electrophile. So how would I get my electrophile? As I mentioned, all acetates are water soluble. And another thing that we know, when you dissolve an ionic compound in water, what would you expect to happen, guys? They dissociate. Ions are going to be separated. Remember, we are talking about electrophilic addition. The reaction starts with an electrophile. Now that I have my electrophile, it is not reversible reaction, by the way. So electrophile is going to add now. Before I complete, I'm going to ask you, mercury belongs to which class of elements, guys? Metals. Carbon belongs to which class of metals? Which class of elements? Non-metals. Between metals and non-metals, which one would you expect? They be happier to be positive. Metals. We know non-metals are more electronegative. Now, why am I telling you this? Because obviously when I am taking the pi electrons, I am taking it away from carbon, giving it to mercury. Would it be possible for mercury to stay neutral and in presence of the carbon cation? Absolutely not. And these are the start of a lot of reactions that from now on you are going to see over and over and over. Electrocyclic reactions. We cycle electrons. We give electrons with one hand and we are taking them away with another hand. So what will happen? And also I want to point out, are you noticing I am taking electrons almost from the terminal carbon? Okay, because electron densities are more toward the terminal carbons. They have less electron pushing groups. Internals, they have electron pushing groups. So they can stand to be positive. That's why you have a secondary cation that can form, but you cannot have a primary cation. So generally, when you are taking electrons from pi electrons, you are taking from less substituted because it has more electron density. When you are getting positive charge, you are getting on more substituted carbon because it can stand the positive charge better. But here, anyway, you are taking electrons away from carbon with one hand and returning it with the other hand. So you really are never going to have a carbocation. No carbocation means what, guys? No rearrangement. So we have eliminated the rearrangement from this. That now look, what do you have? How many members?
3.
3 members. Are these stable?
No.
They know better. Especially when is positively charged, is even worse. So now the nucleophile comes. Which the nucleophile is what, guys? What is the nucleophile? What? Now, which atom would you expect the nucleophile attacks? Terminal or internal? Just always try to imagine which of the 2 carbon would like to be partially positive or more positive. Is that right? Because again, this atom is electron deficient, is taking electron away. Which of these 2 carbon can give it more electron? Terminal or internal?
Yes.
Internal. That's why this carbon is more positive. And these guys, only I am giving you, hopefully you pay attention to size. I am saying that obviously we have a drainer, okay? That positive charge is draining electrons away from carbon. But internal carbons, because they get help, they can be polarized a lot more. That's why when water comes, it comes to your internal carbon. Again, as before, I am not going to tell you what happens here. If oxygen is positively charged, what would you expect? You expect it loses. Okay, and this time, guess what? Even it is okay to use acetate to take the proton away. Tell me why this time it is okay to use acetate, guys. Is acetic acid strong acid? So it is okay. Either acetic acid or let me go down because I don't take it. So either acetic acid or water. Either of the two will come and take the proton. So when they take proton, if you use acetic acid, you will get, if you use acetate, you will get acetic acid. If you use water, you will get hydronium. And you will get your alcohol. So I got my alcohol. What should happen next? We have to get rid of mercury. So that's the time we are using the reducing agent. From your Chem 118A, I will remind you, sodium borohydride is a reducing agent. That's the only thing you will use it for. You have a hydride, that's what you call it, borohydride. Hydrogen that has high electron density. So what will happen? Your hydride will come and, let me do it the other way, is easier to do for you guys to see. It is literally SN2 reaction. The hydride will attack. That will be the driving force to release the mercury. Okay. So mercury is going to be reduced. You will get your acetate and you will get your alcohol. Okay, now that I got where I want to, what would I add? Plus an enantiomer or R and S. As you see, this is a stereocenter, guys. I'm not going to remind you anymore. From now on, it is your responsibility to recognize. If you are generating a stereocenter, you are going to generate R and S. You cannot prepare a pure enantiomer. Always is going to be mixture. So this is Markovnikov addition of water. Now, how about if I want to get less substituted alcohol? I want the other isomer. Which obviously is going to be anti-Markovnikov addition. How can I do that? Now keep in mind, the reason that we are calling it anti-Markovnikov, it is only from the viewpoint of water. Because as I told you, water, we said we look at it as H and OH. So when we are talking about anti-Markovnikov, we are saying that at end, the end product, OH is bonded to less substituted product. That's all it means. So again, we have to do the reaction in 2 steps. Step 1, hydroboration. Step 2, oxidation. I hope you are noticing the steps are exactly reversed. In mercury, oxidation was first, reduction was second. In anti-Markovnikov, reduction is first, oxidation is second. So how does it work? Step 1, hydroboration. Okay, first I have to tell you, boron, B-O-R-A-N-E, boron. Obviously it is being made from boron, so I don't want to be confused. Boron. Boron is element, boron is compound. Unfortunately, it's very poisonous gas. Yes. And commonly, I don't know if you can see, there is something special about DH3. What is special about DH3? What is special? Yes, sir. It has empty, absolutely. It has empty orbital. It's not following empty orbital. Which you call it any substance that has electron deficiency, you call it oxide. You can give it 2 names. What are the 2 names? Electrophile or acid. Either. Okay, guys? So different. It is Lewis acid, and also it is electrophile. So acids are electrophile, by the way, guys. Don't forget. Acid or electrophile. So step 1 is hydroboration, as I said, because it is electron deficient. Commonly we are using in a solvent that can hold on to that. And the solvents always are ethers. The 2 very popular ethers in organic lab which it is diethyl ether for convenience. Guys, diethyl ether. ET obviously represent in our class C2H5. Diethyl ether is one. The other one that I am using, THF, which stands for tetrahydrofuran. One is cyclic. If you are truly paying attention, the difference is only 2 hydrogens between the 2. Both of them have 4 carbons. Diethyl ether has 10 hydrogens, THF has 8 hydrogens. Beyond that, pretty much everything else is the same.
Professor?
Yes.
So when you say the solvent will hold on to that, you mean maintain?
Acid base.
It won't
it
react
is not.
with it?
No.
At
In
all.
the first place, if solvent reacts, did you call it solvent?
Sometimes.
Then we are calling reaction solvent, say. We are using solvent as a reactant. You know, one of the criteria for choosing solvent, it does not cause me mortality. Only does its job, dissolve. Stay out of the way of the reaction. So, as I said, anytime you are using borane, you have to use ether gas as solvent. So step 1, hydroboration. Step 2, oxidation. Hydrogen peroxide is your oxidizing agent. Obviously, the whole idea is to add water as a reactant and works in basic medium, doesn't work in acidic medium. So, when I do these 2 steps, I get reaction. Again, please be prepared for a very long mechanism to do this. It is maybe longer than the first one. I'm talking about oxidation, oxymercuration. Hydroboration, in my opinion, when it comes to mechanism, is longer. So let's look at the mechanism of this reaction. Well, obviously, we are talking about electrophilic addition. And this time, your reactant from the very beginning is electron deficient. It is electrophile. So, borane, which it is electrophile, comes to the. Now, you heard the other day I gave oxygen a title. What was the title that I gave? Absolutely correct, baby. Now, with boron, I am a little bit mean. I call it ungrateful. And I will explain my reasoning. It's not a secret that BH3 is electron deficient. Is there any doubt that BH3 is electron deficient gas? It has only 6 valence electrons. It's electron deficient. And you are trying to give it electron. And I'm going to tell you, as a matter of fact, one of my professors that later on obviously became my colleague, I'm lucky on this campus. I told you I'm organic product of chemistry department at UC Davis. I graduated from this campus. So one of my colleagues, Professor Maskell, really spent 10 years of his research time on these compounds. And the reason he spent, because we can see that when it comes to carbon, carbon can form all types of bonds. And that's why you have diamond, you have charcoal, you have graphite. So boron to him looked very much similar. So he was hoping to be able to make compounds similar, and that's why he spent 10 years literally of his research time, as he said it at the end, they all went down the drain, which I did not agree with him, because I said the others learned, and they didn't repeat what he did. And I mean it, lots of extra, because it is obvious this atom needs electron, constantly screaming, help, I need more electrons. So you try to be nice, and you bring electron to give to it. But as soon as you start to try to give it to electron, look at you and says, look what you did. You made me miserable. If I wanted more than 6 electrons, I would have more than 3 valence electrons. I don't want it. Take them away. And between you and I, we have learned from experience, if you are wasting 10 years of your research time and you are not making this to accept, I say, okay, you don't want it, I take them away. How can I take it away? Do you see another electrocyclic reaction? You take electrons with one hand. What are you doing, guys? You are returning with the other hand. Okay, guys? So again, you are taking electrons from less substituted. You are returning to the more substituted. So this is the first step of reaction. Dotted line means what? Bonds in transition. Either you are making new bonds or you are making old bonds, guys. So keep in mind that. That's the meaning of dotted line. So the first step, and everything really is one-step reaction. They are not reversible, guys. They all go, either they go or they don't. They are not reversible. Okay, look here. What do I have? Again, the same atom, which is electron deficient. And obviously you have alkenes around, don't you? So what it means, two more exactly the same step. Okay? Exactly two more alkenes. Same thing, nothing new. That's why I am not going to rewrite each of them. So when the reaction is completed, and obviously you are going to have three of these aggregates. Okay. Now, for convenience, because these three groups are, all three of them are identical. Only for convenience, I am going to define the part that I have circled as R, because they are not going to do anything yet. So, CH2, C, trimethyl group, guys. I am defining R because all three are identical. And this is, again, I repeat, only for convenience, no other reason. One thing I have to tell you, these compounds try alkyl borane. Whatever the name of your alkyl is. These compounds are stable. You can isolate them. You can bottle them. You can sell them. So you can run or NMR, you name it, guys. Anything that you do with a stable compound, you can do with this. But this is not what I want. So this is step one. Now, step two, which it is oxidation. Well, we have hydrogen peroxide and we have hydroxide, which it means acid-base reaction. Now, naturally, this is a nucleophile, negatively charged. And as you know, your boron in borane compound is electrophile. electron deficient. So what it means? It means that the peroxide is going to react with acid-base reaction. Lewis acid, Lewis base reaction. So the nucleophile is going to attack. Non-reversible reaction. Now, let's see what we have. Is boron happy to be negatively charged and have 8 valence electrons? Absolutely not. Is oxygen happy as a peroxide? No. So here I have 2 unhappy customers. Boron is nagging. I am not that electron negative. Why do I have 8 electrons? Oxygen is extremely upset. How could boron have negative charge in presence of me, for which I am so weakly bonded to another one that I really don't like? So they nag enough that we will say, okay, there is no reason to nag. You are not happy, they make you happy. That's what OCHEM people do. Okay? Remember, rearrangement. And when we talk about rearrangement, truly any group could migrate. So rearrangement happens. And the reason that I kept one of the carbon because I want you to see it like this. Okay? Because you see, if I was just going to take that electron away, would oxygen let me to do it? This time it stands in front of you and says, over my dead body. And it is serious, guys. Oxygen doesn't mind to be positive as long as it has 8 valence electrons. Absolutely is not going to be humiliated to be positive with 6 valence electrons. So migration probably even has started already before you break the other one. So one group is going to migrate. Again, what would you expect? Electron deficient? Peroxide ion? Rearrangement. So, I will say 2 more peroxide, 2 more rearrangement, because again, every step is going to be exactly the same. So when it is done, we are going to have boron that it is being surrounded by 3 trialkoxy group, guys. Okay, so we are going to have trialkoxy group. But keep in mind, your medium is what kind of medium, guys? Your medium is basic. Boron is electron deficient. You have strong nucleophile base. Guys, my apology. Either I can squeeze them here or I need to erase them. What should I do?
Erase.
Okay.
Professor?
Yes.
So boron is bonded twice over here. Okay, should it not have some type of a charge?
Anytime boron has 3 bonds,
Two. Okay. Twice. Only two bonds.
C2,
Right. Where's the third?
RC2.
This one?
Yeah, she's still on the right.
look at her notes.
Oh, okay. Never. Thank you. More copies.
So, what will happen now that we have peroxide, oxy, boron, the hydroxide is going to get there. So I'm going to write it this way. You know, I try to keep them as long as I can available for you. Ladies and gentlemen, is boron happy? Okay. So now it's going to speed them up. You know, it had tried everything it could. So what will be next? Because this time it really can't do anything. So it is going. And one thing I am going to tell you, I don't know if you do remember the principles of acidity or basicity from 118A. When it comes to alcohols, water generally is stronger acid than alcohol. The only alcohol that it is stronger than water in acidity is what, guys? Methanol, which obviously we cannot make methanol like this method. Water is generally stronger acid than alcohol. General chemistry, you were told, again I always with my own version, stronger acid liberates weaker acid. I like to call them liberator, guys. Or stronger acid generates weaker acid. Either, okay? I call them, so from now on, anytime you hear liberate, you know what I'm talking about. So what it means that water is acidic enough to protonate. Please let me write it the way it was. That's the only reason I kept it. So you see it's okay. So your alkoxide water is stronger acid than alcohol. So water will protonate an alkoxide into alcohol. Okay, guys? But then, what do we have? We still have 2 more alkoxy. Having 2 more alkoxy means what? 2 more hydroxide, 2 more water, and that's what I'm going to do. 2 more hydroxide, 2 more equivalent of water. So I will get a total of 2 more alcohols and DOH, OH, OH. Now, general chemistry question. What is the name of H3BO3? It is boric acid. What is your medium, guys? Base. So, the fate of the boric acid depends on the amount of sodium hydroxide. If you have large excess of sodium hydroxide, so I'm going to write large excess of sodium hydroxide. A large, yeah, I have to say yes. Large excess of sodium hydroxide. You can neutralize boric acid to sodium borate. If you don't have large excess, then you are going to get NaBOH4. So nobody cares about boric acid, guys. That forms. When nobody cares about that, it's not organic. We just care about organic. By the way, sodium borate is unclear. So you know it's not that expensive that we even care about it. So that makes sense. So this is the mechanism of addition of water. So I hope you are noticing when it comes to alkenes, these are, oh, amazing. I just managed to get on time. We can make any kind of alcohol we want without rearrangement. With rearrangement, more substituted, less substituted, which it means tomorrow we will finish chapter 12 and I will move on to chapter 13. Have a nice day.
Wait, so do we have 19 reactions already?
Huh?
Like all of them are like 19 reactions or part of it?
Yeah.
Okay, thanks.